maybe the ideal watches.
So this is my work with my PhD student, Krzysztof Lorek. And it's also somehow linked to my previous work with guys from Sweden and England. And it's basically about quantum effects in relativity. And I would like to start with a quotation from this nice book by James Hartle. Very, very nice book, like first manual, like introduction to gravity. And they mention the idea of so-called ideal clock, which is a device, hypothetical device that measures proper time along a path. So basically, if you have a clock that moves with constant velocity, special relativity tells you that it's going to be delayed by a certain constant factor depending on velocity, and the same factor, it's the same factor for all possible clocks. So no matter what device you take, if it moves with velocity v, the dynamics is going to be slowed down by the same Lorentz factor. However, if you take a clock and make it accelerate, special relativity doesn't really tell you what's going to happen. For example, if you take a pendulum clock, something else is going to happen to it. Then if you take an iPhone that also has a watch in it. So the mechanism of the clock can, specific mechanism can behave differently for the case of accelerating motion. It's a little bit in a contrast with what this guy is saying and with what most textbooks is saying about that issue. So they are giving a formula for proper time, which is basically an integral over time with this Lorentz factor. And let me notice that this expression does not depend on acceleration. I'm going to talk about that in detail. It only depends on instantaneous velocity of a device. And proper time is this so-called like length of a path in space-time, four-dimensional length. And what this guy is saying that it should be noticed, emphasized, that these expressions hold even for accelerating clocks, even when the velocity is dependent on time. So they say that ideal clock can actually measure this thing if it accelerates. And there is a famous test of this relation for an accelerating clock, and it's described on another page. Let me just tell you what the test is. Basically, they have a decaying particle that moves with very high velocity and moves in a circle, basically in CERN, in the accelerator. And moving on a circle means accelerating all the time. And actually, these accelerations are quite high. The experiment apparently measures accelerations up to 10 to 15 or even more g, which is quite a lot. And apparently the decay rate of a muon is affected by the Lorentz factor exactly according to this formula, and no corrections to that formula are discovered in the experiment, even for accelerations up to 10 to 15 g. So apparently the decaying particles are very good ideal clocks that actually are able to measure this relation. Now, my talk is basically the purpose of this talk.
Perhaps that's not the general case, because in the accelerator, v squared is constant.
That is true. Yes.
Therefore, this is not the general case where you have v
That is true.
square changing.
That is true. So so I can't actually study this. I'm not studying this example in this talk. I'm studying the example of linearly accelerating particle, and the purpose of the talk is to show that actually every clock has to break down at some point, and every clock has to eventually depart from this formula. That it's not possible to have a device, physical device, that actually can measure proper time along any path. So the example what I mentioned before is that different clocks will behave differently for the case of acceleration, and you have to ask yourself, how do you actually build a device? Which clock mechanism do you choose to have a device that measures proper time regardless of its acceleration? And one thing I would like to notice is that this formula can't actually be derived from special relativity. You can't really derive the rate of accelerating clock. What you're saying is that if you have a clock that moves on a path that is curved, you approximate that path with a bunch of straight lines, and you say that on those straight lines, obviously the clock rate is known, it's just delayed by the Lorentz factor, but you don't know what's going to happen on those points where the acceleration is actually infinite. And you're saying nothing happens there. That the clock is not affected by those points. That's your approximation. And you approximate the real mechanism by saying that it's actually the same as being converted into a bunch of straight lines.
No, but what's wrong with this formula in the continuous version? Why do you deny the significance of this formula?
Because it does not depend on acceleration. In principle,
So
behavior...
So what? I mean, it's still the proper time.
It is the proper time. So that's the mathematical formula. That's the length of the path in space, right?
Yes.
But the question is, can you have a device that actually measures it? Which means, can you have a device that is completely insensitive to acceleration? Is it possible? All devices that we know are affected by acceleration. If you take a pendulum clock and make it accelerate, it's broken.
What about elementary particles?
Exactly. So the most fundamental clock you can think of is the elemental particle that's decaying. If even decaying particle turns out to be affected by acceleration, in contrast to this formula, then I should say that there is no way of building an ideal clock at all. Even if elemental particle that decays and that decays is used as a rate of proper time, even if that is not a good clock, then I guess we can say that there is no way of building a good clock that actually measures this. So
this assumption that nothing happens at these points
yeah.
is the origin of the twin paradox, simply. Because in twin paradox you have the same. You have the velocity in one direction, then instantaneous change of the velocity to the opposite one, and then you have twin paradox. So you cannot assume that nothing changes at this point.
Exactly. Well, with twin paradox is a bit different because, well,
because you change the velocity, so you are not in the
No. But in twin paradox, you actually, even if you have a twin that measures proper times, there is already a paradox, right? And paradox,
it's because of these points.
Because of these points, yes.
Yes.
But what I'm saying is that if you have acceleration like that, your clock is not going to measure proper time. It's not going to be even proper time. It has to be something else. There has to be corrections that depend on acceleration, and I'm going to show that there must be these corrections.
But in the twin paradox, we don't have to introduce such sharp changes.
No.
It's just two different paths.
Yes.
When the twins come together
Yes.
continuously, there will be a twin paradox.
Yes, of course. But let me put it this way. In the twin paradox appears already when you say that you have two clocks that are able to measure proper time. What I'm saying that even measuring proper time is not possible. So let me just give you one example. I always give it to students to make them realize that there is actually a problem.
To make it completely clear, it's not important that these changes are discontinuous.
No. Even for continuous
Yeah.
motions, there is going to be a problem. So consider a very simple type of motion, a sinusoidal motion when the clock is actually oscillating. So the trajectory is according to this formula, velocity is its derivative, and acceleration is the second derivative. And I can consider the following non-relativistic limit of that motion, where amplitude goes to 0, but frequency goes to infinity, in such a way that the product goes to 0, which means that both position and velocity go to 0. So the clock is technically resting, but I can take the limit in such a way that a times omega squared goes to infinity. I can always find a transition like that. It doesn't have to be infinity, I can make it sufficiently large, that's enough for me. In that case, position is strictly 0, velocity is strictly 0, acceleration is singular. It's oscillating very fast with very, very high amplitude. And, sorry? And
A is going to 0.
No, but the
it's not
amplitude,
The acceleration is huge.
amplitude of acceleration.
Okay.
a times omega squared goes to infinity, which means that you have a device that is almost at rest, but it actually accelerates like crazy. And then you can ask yourself, suppose you have a second clock that is just doing nothing next to it, standing still. And you ask, is the rate of these two clocks going to be exactly the same or not? So you have a clock at rest, and and the other one that is accelerating very, very fast, infinitely fast actually, and switching the direction of acceleration infinitely fast. And if that's ideal clock, it should work exactly as the one that is standing still. Now, is it possible to have a device that is insensitive to infinite accelerations? I don't know, I think not. Well, actually I know, and I want to show that it's not possible, but this example already should make you doubt a little bit about the possibility of using this formula, because according to this formula, this infinitely accelerating clock should go exactly as the one that is standing still, because there is no acceleration here. It doesn't care about acceleration. So, yeah, the question is, can you measure this? Can you have a device that you use to measure this? Now, there's another argument why this is a very good way. I mean, this is this idealized notion of time, simply because this expression is invariant under Lorentz transformation. Which means, if I have a path in space-time, maybe it's good if I draw this on the blackboard. If I have any path in space-time, and I measure proper time, or calculate proper time between A and B, I get a number. This number is insensitive to Lorentz transformation, which means if I go to another frame of reference and observe the same trajectory from a different frame of reference, which is going to look maybe somehow like this. So it's the same path but viewed from a different by a different observer. A and B is here. If I calculate proper time here and proper time here, I get the same number. So people say that ideal clocks must be measuring something that is insensitive to Lorentz transformation, because, well, as all measurements, if you make a measurement, get a number, this number cannot depend on the observer who is actually looking at the device. And proper time actually has this property that is invariant under Lorentz transformation. But I'd like to say that this is not the only invariant that characterizes the that characterizes the path in space-time, and this is not so well known. I'm surprised I never found this in any textbook. But I can give you a simple example of other invariant along the path that depends on acceleration. So take for acceleration, which is basically derivative for velocity over proper time, and take a square of it and integrate it over proper time. Since this square of a 4 vector is invariant under Lorentz transformation, and proper time is invariant over Lorentz transformation, this whole integral is also invariant. Actually, it turns out to be proper acceleration integrated over proper time. Proper acceleration is acceleration experienced by the co-moving observer. And if you do simple transformation, you get this integral. Now, this integral also does not depend on the observer. You can Lorentz transform it and you get the same result. So, and more than that, this is actually dimensionless. This has no dimension, no physical dimension if you divide it by c squared. Or if you divide by c, it's dimensionless. Which means that you can easily modify this formula using that invariant and get some other expression that is invariant under Lorentz transformation. Which means that you don't have to stick to this formula. Maybe other devices that are insensitive to Lorentz transformation can be built, but they do, depending on acceleration. So
why would you call it time?
Well,
you didn't really explain the basic question. You
Yes.
say that this is not the right formula for time. So what is time?
no, I'm not saying it's not a good. Actually, this is the best formula for time. It's this the assumption that the common assumption in general relativity is that this is actually time. But the question is, how do you measure it? I'm saying you can't really measure it.
But how do you define time that you want to measure?
This way.
This way.
This way. I'm trying to build a device that measures this, and I can't. I'm saying that every device is going to measure something different than this. And there is no way of building a mechanism that is going to measure this. So if you want to call this time, I'm happy with that, you have to accept the fact that there is no way of measuring it. So in a way, the definition of time this way is not so meaningful. I mean, I'm talking about the range of extreme accelerations. Obviously, in the limit of small accelerations, you can measure it perfectly well. This clock is in a gravitational field, which is in a way being accelerated with a small acceleration, and it still measures proper time. So within certain limits, it makes sense to think about this as a measurable quantity that you can call time. I'm saying in a huge acceleration limit, it's not possible. And the reason for that is very, very simple. The reason for that is the Unruh effect, which I'm going to tell you about a little bit. The Unruh effect is something that people get interested in a lot these days, but already Richard Feynman was quite interested in that. This is Feynman's blackboard that he left in his office, and he never went back from the operation that he took. And somebody took a photograph of that blackboard that he left in his office. And he left some remarks what he wants to do. For example, he wants to know how to solve every problem that has been solved. That's his agenda. But also, on a short time scale, he wanted to learn something about other physical effects, like 2D Hall effect. But also, he wanted to know about something that he named acceleration temperature, which is exactly the Unruh effect I'm going to tell you about. So the Unruh effect is the following stuff. Imagine that you want to observe a photon of a given color, green photon. What it means, you have to have a certain device and a certain observer that actually measures with some device that photon, and they get certain outcome. But if you get another observer that's moving with constant velocity, he's going to see the same photon of a different color. So if she sees the green photon, this guy could see a red photon, or any other way, Doppler shifted photon. So the photon is still there, but it's going to change the color if you change the frame of reference. However, situation changes dramatically if you replace this other observer that was inertial by a non-inertial observer that accelerates. In that case, this observer not only sees a different color, but he even sees a different number of particles. She can see a single photon, but this observer can see other number of particles. Even if she sees the vacuum, if there's no particles, from the perspective of this observer, this guy is going to see some particles, and actually if you do the math, you find that this guy is going to see a thermal state of particles with the temperature proportional to proper acceleration. That's the Unruh effect. So, I mean, it has very nice, interesting philosophical implications. For example, you would like to think about particles as real objects that are objective somewhere, but those real objects actually their presence depends on the observer. So one observer sees them, the other could say that there is no particles, or vice versa. So there is no such thing as an objective object. I mean, objective, whatever, phenomenon that does not depend on observer. Even the particle number depends on observer. So if you have an atom, somebody else could say that there is no atom at all. And that's the Unruh effect. And not only the vacuum state transforms this in this non-trivial way, but every quantum state actually transforms itself into something else when you if you change the frame of reference in general. And the Unruh effect is this special case when the initial observer sees the vacuum of some quantum field, the other observer is going to see a thermal state full of particles. So let us go back. Let me just briefly tell you what I want to calculate, and then you understand the idea. You can leave the talk if you want, because basically you will be able to understand why no ideal clocks are possible. Suppose that we want to take a decaying particle as the most fundamental clock, that is our candidate to something that measures proper time. What does it mean to have a decaying particle? This is some sort of excitation of a quantum field that interacts with another field, and that interaction leads to certain transition of the initial state to some other final state. For example, you can have two fields. One of them has a single excitation, that's your particle. The other field is in the vacuum state, there is no particles, they interact. And after a certain time, there is a probability that your initial particle disappeared and reappeared as the excitation of the other field. For example, muon can decay into electron plus some photon. So in QED, this process is more complicated. It involves more than two fields. But you can imagine a very simple model of interaction. You only have two fields, and one of them decays into the other one. Now, this decay rate is obviously affected by the initial state. For example, if you have a single excitation of field number 1 and no particles in the other field, you get a certain decay rate. But if you have this other field being occupied by particles, the decay rate is going to be affected. That's clear. Now, if you have a decaying particle, you can calculate the decay rate, assuming that the other field is in the vacuum. However, if you make that particle accelerate, from the point of view of that accelerated particle, the other field is not in the vacuum anymore. It's filled with thermal particles. So the decay rate is going to be affected. And since those thermal particles are very, I mean, the number of them is very small, for small accelerations you don't experience that. As long as you accelerate not too much, such that the Unruh effect is not evident, you're not going to see any effect of that. However, if you turn on very strong accelerations, the accelerated particle is going to experience the surrounding field as a thermal state, and the decay rate is going to be clearly affected.
But the problem with decaying particles is that the decaying particle is not a well-defined state. It depends on history. This is just a resonance. And resonance is not a state, but it's simply continuum.
So in other words, the definition of the initial state is a little bit ambiguous.
Of course, this is a problem, so that's why people do S-matrix formalize in particle physics to avoid those problems. And what I'm studying here is the long time.
But this is only an approximation.
Yes, this is an approximation, of course. So what I'm going to go into details of that, but I'm calculating the decay rates for long interaction times. So I assume that I have a certain initial state, and then I calculate interaction, and I calculate probability of some process.
Are you using the of exponential decay?
Or power law.
Yes.
Well, that's a big difference.
I'm taking the perturbation here, obviously, and I'm doing the second term.
So the decay rate is slightly insensitive to the definition of the initial condition.
So the probability of decay
is very short Z0 part and the polynomial part, the algebraic part, which are dependent.
So in the regime I'm looking at is that the probability of decay is linear in time. So
which exponential?
No, it's the decay rate is constant.
Yes. And that leads to exponential decay, not to be.
Yes. I mean, there is a subtlety, but probably yes. It's the perturbation
Well, the
regime.
point is that, strictly speaking, for a very short time,
yes, exponential
it is not 1 minus gamma t. There is a deviation.
Yes, I know.
Leading to this quantum zero effect.
Yes. Well, you don't necessarily recover that when you do. That depends also on the model of decay that you have, but.
And for long times, again,
it is tricky, yes.
Okay. So let me tell you about it. So basically the idea is again this. If you take any object that has certain dynamics, could be a decaying particle or anything else, you make it accelerate. At some point, this accelerating object is going to experience a thermal state around it. And that's inevitable. The more you accelerate, the higher the temperature. And eventually, that temperature takes over all processes.
But the main problem now that you encounter is, what do you mean by accelerating the particle? How do you accelerate it? What kind of force you apply to it to accelerate it? And this will be the crucial problem.
Yeah.
Because this will certainly depend on the way you accelerate the particle. How do you accelerate the muon?
Yes, good point.
Applying a certain field. The field means that there is an exchange of photons, etc.
So, but that even adds more problems to what I'm already saying.
I think this is the main problem, because when you think of acceleration in classical terms, you visualize this, that you have a rope and you pull by this rope, and the vessel accelerates. But for a particle, you cannot do that.
Of course. You're absolutely right.
So you have to even go one step back and say, what is the acceleration mechanism? And that will depend on the acceleration mechanism.
I absolutely agree. So,
you should take a more or less realistic model. Let's even take the simplest one, when you have electric field which you apply, and then you have a model for acceleration.
Well, if you want, so let me put it this way. If you do that, which you can do obviously, you get into even more serious problems that I'm saying. So I say that even if you forget about these problems, these practical issues, you already run into troubles trying to measure proper time. If you actually try to be more specific and more physically correct, you get even more problems. For example, you want to switch on constant electric field to accelerate the charged particle. You have to have very, very strong electric field to accelerate it very, very strongly. which means that you have to have very, very strong energy densities in your electric field, which is going to inevitably create some extra particles out of the vacuum, because the energy density is just going to be too high. So in a way, that is going to even to break down your mechanism even stronger than what I'm saying. Because if you just crank up the electric field too much, it creates antiparticles and particles, and that distorts all the interactions. Yeah. So you could also try to think about classical potential. Then suppose you have a particle in classical potential and treat the potential classically, and somehow change the potential, make the potential accelerate. That could be something.
So maybe that indicates that there is no answer to this question.
Yes.
Because you cannot realize it.
Yes, that's exactly my point. That's exactly my point. I'm saying that these problems already appear on this level, but there are even more serious problems or more severe problems that need to be taken into account. And the message of this talk is that despite the optimism of James Hartle, who said that proper time can be measured and that has been proven up to accelerations 10 to 15 g, I'm saying that if you increase a few more orders of magnitude, because I would expect that already at 10 to 18 g you already start to see the problem deviations. Despite of the optimism of the author, I'm saying that it's not possible to measure that quantity. And you just have to forget about the idea of time, of measuring time for high accelerations. What does it mean physically? I don't know. Because
why do you want to measure this? You measure physical effects.
Well, yes, so you want to say that time is not a physical effect at some extent.
No, it appears in various contexts. For example, it appears as a lifetime of a muon.
Yes.
And you can measure the lifetime of a muon when muon is being accelerated.
Yes.
And that's a physical problem, and I don't see why is that.
Regardless the implication, it's kind of interesting that the accelerating muon decays differently than just moving muon. I think it is interesting.
The consequences are very serious, because if you can't measure time, you probably can't measure space as well, because these things are related. And what I'm saying is that physics of non-inertial frames, extremely non-inertial frames, is probably going to be completely different from what we know in our presence when the...
That's because the theory is not invariant under such transformations. That's a very simple question. There is no theory that you can apply here.
I mean, well, there is theory.
Field theory does not apply to accelerated frames of reference.
Why not?
Because it's not invariant under general
but
transformations. So you cannot say what is the vacuum.
Well, I think the Hawking effect and the Unruh effect and dynamical Casimir effect and many other effects are based on the assumption that you actually can take quantum field theory and put it on the non-inertial frame of reference. So people believe, well, those people believe that to some degree you can actually do it. You can take
a Hawking effect is something different, because the whole system is stationary. There's no time. There is no time dependence in the metric.
There is. What?
The metric is
Hawking,
time dependent.
In Hawking's calculation, he has a cloud of dust that is collapsing, and that's the technical background.
The original Hawking idea
Yeah.
was that when you have a horizon, then particles are being produced.
The original Hawking's paper.
Pairs.
The original Hawking's paper is dealing with the collapsing dust. And he specifically says why he does not consider eternal black hole. There are good reasons for not doing that. It's actually more complicated to consider eternal black hole than the collapsing star. Simply because you don't know how to choose the initial state.
And the boundary conditions.
Yes, exactly. And when you have collapsing dust, there are boundary conditions in the past and in the future. So you can use them. So Hawking actually believed that he can take quantum field theory, put it on extremely curved space, then where you have a singularity in it, and still do your quantum field theory calculations. So obviously we don't have certainty that still works. The theory still works. It could be breaking down. We don't know. But certainly there is no clear way of saying that this cannot be applied. We don't have experimental data for it. So as long as we don't have experimental data, we just assume that we can apply the theory to the context that we have never tested the theory. And some of us believe that it works. that belief leads to Wunner effect, that belief leads to Hawking radiation and other effects. So I'm going to take that assumption and say that already that assumption leads to the problems that I heuristically argued. So, yeah, so I'm considering a very simple model of a decaying particle. I'm considering two fields, two scalar fields. One of them is massive, one of them is massless for the sake of, due to some technical issues I don't want to go into. So I have two quantum fields. One of them I'm denoting with capital phi and capital quantities, and the other has a decomposition into plane waves and annihilation operators with small letters.
These are free.
Yes, these are free fields. And I'm switching on the interaction of the most simple form I can think of, basically a product of two fields and some coupling constant.
So really there is no interaction because you can diagonalize this whole thing, it's quadratic still. So you just change the modes, and that's all.
Yes. Well, but you call it, well, but this is the interaction. Quadratic.
But this is not really interaction. You have two coupled harmonic oscillators, and that is equivalent to a harmonic oscillator.
Okay, why do I call that there is interaction? If I have a single excitation in one of those plane waves, this is the diagonal base when there is no interaction. If I have a single particle in this one of those plane waves,
then it's not the eigenmode of the whole system.
Yes.
You should use eigenmodes of the whole system.
yes. But well,
So you cannot have decays in this setting, because this is not...
well, you can have a decay if you interpret a particle as an excitation of that mode.
But these modes are not
But it will
physical
come
because
back.
you have coupling.
Well,
No, it depends
It
what
will
you
come
measure.
back. not really a
it's
decay.
not necessarily going to come back because
Eventually.
This is like two coupled pendulum.
well,
So
infinite number.
Yeah,
of
infinite numbers. So
Yeah, for that reason.
Infinite number, so if you
Yeah.
so there are photons which goes to infinity.
Probably you say that you want to square somewhere to make it more.
Of course,
Yeah.
if you want to have real interaction.
Of course,
Otherwise
yes.
it's just two.
The reason I'm not making it more realistic, well, if I wanted to make it realistic, I would just take QED and take a real interaction. It's just I want to show something much. This is
No, but I'm afraid that in this model you don't really see what is important here.
I think I do. I think
Because there is no decay.
Well, let's see what.
No, but the situation is not so bad, I think, because one field is massless and the second field
Is
has mass. So it is not as simple as you say. Because then
It is still a quadratic system.
yes, it is quadratic, but if lambda is, but it is almost, it is almost.
Polarities are of the
Yes.
same type. It's a massless with massive and so on. You still can diagonalize.
You still have.
Yes, it can be diagonalized, but
Yeah, sure.
no. You
So
can
it's not unusual at all.
You can diagonalize.
You can diagonalize. That's I agree with. But
So there is no decay.
well, if depending on what you call a particle, if you
Yes.
call a particle excitation of
Yeah,
your
sure.
eigenmode of that
Yes.
system, then there is no decay. You're absolutely right. But if you take a particle to be an excitation of this mode, then there are decays.
But it will come back. It will decay.
Eventually, it will
But it will be until
Very
very long time until.
this time it's actually.
So this is a phenomenon which has a closed system, for example, and we do not bother
Yes.
too much with that.
If that field is quantized in a box, if they are both quantized in a box of the same size, then they are going to be
Yes,
boundaries.
yes.
But if this is a free field with no boundary conditions, then there's no going. The revival time is infinite. So
Then
But
there
the
are
students-
integrals, not sums.
yes. So the sum is just symbolic. So again, it's not a realistic model because first of all, there are no useful massive fields that interact in this way. It's just a model of the interaction. I'm arguing that the same thing you would get in QED if you do a proper hardcore QED calculation. It's just going to be more time consuming and it takes more effort, but the effect is the qualitative answer is not going to change. And I'm going to show this qualitative answer just to show you what's going to happen roughly with this type of interaction. You are going to really see what would happen if you take more serious interaction of other types. So what we are doing, we are taking this, we are taking first order perturbation expansion, and what we calculate is the probability of a transition from the single excitation of one field to whatever in the final state, provided that there is no particle in the initially excited field. And I'm going to bring up some extra problems that should be taken into account. First of all,
are you restricting yourselves to lambdas for which the whole thing is bounded from below?
If lambda is sufficiently small, it's always bounded from below.
That's right.
Yes.
But if it is sufficiently large, then it will collapse.
Yes, yes. But there's one more thing I haven't discussed yet. When you think about particle, you think about a localized object. And when I draw this line here, it's a path of a clock. But no real particle can take a path, simply because there are no point-like particles. I mean, electrons are considered to be point-like particles, but they always are localized within a wave packet that is actually spreading. Even if you forget about the spreading, you can't over-localize an electron, simply because if you try to squeeze it too much, you put again too much energy in a single point, and the density of energy becomes so high that you create particles and antiparticles. Yes. So you are going to destroy your clock as you try to shrink it. So you can't shrink your electron too much. You have to have a balance. So that means that the electron or your clock doesn't actually go on a path, it goes on a smeared path. That's actually spreading. And even if there is a way to avoid that spreading, I'm going to talk about that, it's not a single path. And moreover, if you want the size of the electron, of the clock, to be fixed, in a way you want the electron to be rigid from its own point of view, it means that both different elements of that wave packet has to undergo paths that have different proper accelerations. So there is actually a bunch of trajectories you have to consider that are bundled. They are characterized by different proper accelerations, and you see things are more complicated. You can't localize it too much because you break down your clock, but you can't localize it too little because then there is no single path for you to characterize. So there is some sort of trade-off between those things, and all those effects you have to take into account in that type of calculation. So since I want to make life really simple, I don't want to bother with the spreading, I'm assuming that the particle actually is put in a box, and that box is accelerated. The box is classical, it has a certain boundary condition, and I accelerate the whole box. And there is particle inside. And the control over the size of the particle, I have that control by controlling the size of the box. And that's basically the idea. So what I'm doing, I'm placing one of those particles in a box. There's a single excitation inside the box. The other field is free. The box is transparent to that other field, and those two fields simply interact. And I'm calculating a probability transition of.
But what happens to energy and momentum conservation? If one particle is massive, it can never decay into massless particle.
Well,
because of the energy and momentum.
That is obviously true. You can't. Photon can be absorbed by an electron. But why do you expect momentum conservation here?
Because there is no external force.
There is, because you make the particle accelerate.
No, but without acceleration,
yes,
there is no decay. Particle cannot decay because of the.
No, if you have a particle at rest that is massive, it only means that you are going to have a symmetric decay into right and to left, right?
No. What do you mean? It decays into one particle, not two particles.
Yeah, but there is amplitude for the particle to be created to the right and to the left.
No, that's not the way it works. So you say that two particles so it decays into two particles, that would require phi squared.
Yes, in QED you would have to have that process on shell, right? But this is not the case. So again, you violate that one more thing. You may not like that so much, I guess. It's not a physical process, yes.
But you cannot get it from the calculation. The calculation, if you do it properly, will preserve the energy conservation law and momentum conservation.
Okay, let me tell you what I'm calculating explicitly. That's a very good point, actually. I haven't thought about that.
Of course, if you have short time, then you don't have to conserve energy because of the uncertainty principle.
Yes. So,
but if you wait until the things settle, then you see that there is no decay.
let me say what I'm doing. I'm taking the evolution operator, which is basically e to the minus IH t. I'm expanding it to the first order, 1 minus IH t. And then I'm calculating the probability of the amplitude of this sword. I'm taking the first field to be a single excitation of a certain mode of the cavity, the ground mode of the cavity. I'm calling this one 0. And the vacuum of the other field. I'm putting here this evolution operator, and I'm calculating here 0 in the first field, and whatever in the other field. Then I'm calculating the probability, which is a square of this, and I'm summing over all betas. So if this is A, then I'm calculating sum over beta.
Does the Fermi's golden rule?
Yeah, exactly. And I'm just doing this calculation, I get something. Obviously that violates the conservation
Sure,
of...
because you are,
It even violates conservation of probability.
yes.
Yes. Well, simply because it's a perturbation theory.
Yes.
How can it not violate it? But again, it's not a proper calculation you really want to do that represents physical process.
Yeah.
But still, the way I'm doing the calculation will, that's this next transparency, will show explicitly that there is an effect that is going to be present in every possible modification of that calculation if you take into account proper
No, if
physical
you,
process.
if you really do it correctly with unitarity preserved, then you don't see this effect.
Yes, that is true, in this model, yes. Well, there are no, first of all, there are no fields of that type. You could already say that this is not physical because there are no scalar fields.
No, but the main problem is this quadratic calculus. If you had two particles, if you had small phi squared, then it can decay into two.
I think it would not be so difficult to modify it on the squares. It's just, it was
If
a
you are
simple-
using perturbation theory, it would not be difficult.
Yes, it would not.
But because this is a quadratic model in any case, so you can calculate it exactly as
Yes.
Yes.
if you want. You
Yes.
don't need to use.
I mean, you can calculate it exactly easily if the number of modes is countable, that only involve some numerical summation. If in the continuous limit transition, it's to some degree it's also possible.
In the continuous limit transition, it's even easier.
Is it?
Yes.
The problem
You use
is
the Laplace transform and you look for the poles. It's a standard calculation.
Okay.
the problem, of course, then is that the Hamiltonian is not bounded from below.
It is
Yes.
bounded if
For
lambda
certain
is,
lambdas.
No,
For certain
no.
lambdas.
for small lambdas it is.
Lambdas has to
Phi squared and phi is not bounded from
Ah,
below.
no, we are talking about this phi.
I'm talking about phi squared.
No, we
because
are talking about
with-
phi. Still staying with his model.
But then there are problems here with this energy momentum conservation.
Look, this is just a toy model. Just think about it as a
The
toy
model
model.
should at least preserve.
Every toy model breaks
principle.
down for that reason or other. I mean,
No, but not the basic law of energy momentum conservation.
Okay, yeah, I'm happy to modify it just for that to be like not to have that problem, but I'm saying that the result is not going to qualitatively change. And let me show you what's the result. So this gamma n is the transition from the this is basically a summation of all possible rate transition from this state to anything else. So this gamma is what I call A here on the black. And when the clock is at rest, this is the answer we are going to get. Now,
Where is the clock here? What have you?
I'm calculating the probability of transition.
Yes, but you are calculating it in two cases. So what's the second
In
case?
first case,
The first case,
he
the box is
assumes
at rest.
that
The box is
everything
at rest.
else is in the vacuum.
The
And
box
phi,
is at rest.
little phi is in the vacuum, and in the other
Yes.
that it's in this Unruh thermal.
In the other case,
Yes.
the outside field is actually in the vacuum state of the Minkowski observer.
Yes.
But from the perspective of the accelerated box,
Yes.
it's a thermal state. It's a Unruh vacuum. It's an Unruh thermal state.
Put in other words, the other thing is just the decay in the presence of thermal field.
Yes. So not so complicated. Really.
Sure.
So, and you can now imagine that if I modify the expression, these formulas are not going to be affected at all. It's only that those gammas are going to be different, and those gammas are going to be different. But those expressions that I wrote on this transparency are going to be preserved. So you can change your Hamiltonian to your favorite one, You can even go to QED or anything else. And plug indirectly those expressions. You just have to replace gammas with the appropriate probability transitions.
Yes.
What is not going to change is the presence of this term, which is crucial for this talk. And if you actually do the calculation for that model, you get certain numbers here. And in the limit of long interactions, this number is going to be proportional to t, which is basically saying that the decay rate is constant. So if you extend it to continuous limits, you get the exponential decay here. And when you have accelerated case, you have also linear dependence on the proper time, but with a different proportionality constant that depends on acceleration. Alpha is proper acceleration. And you can't get rid of it. For small accelerations, this term is negligible, and you approximately have the same thing here and here. Just replacing t with proper time is good enough.
Is there some additional constant here?
This is some constant depending on mass. It's a complicated term of...
No, but in the exponent, that should be dimensionless.
This is dimensionless, yes.
Omega is frequency and
yes,
alpha is acceleration.
Yeah, if c is equal to 1, this is dimensionless.
Ah, C.
C is equal. So, but this is obviously dimensionless. And since omega depends on this, it's the ground level of the box, ground energy level of the box, it depends on the size of the box. So this correction depends on both acceleration and the size of the box. And even in the limit of very small size of the box and sufficiently high accelerations, that correction is non-trivial. Which means that it's not simply enough to replace t with tau. You always get something else. Now, I'm using a specific model of interaction to make it evident, but we also did calculations for other semi-classical approaches, like using Unruh-de-Witt detectors. We always get similar thing. So in a way, this is pretty general observation, that this term is inevitable in whatever type of interaction theory you want to use.
But how do you find the modes in the accelerated box?
Because the uniformly accelerated box has a very nice, the Rindle frame of reference is very convenient.
No. Because acceleration in the Rindle picture goes forever. Therefore, it cannot be used to define the states of the system.
No, because it goes forever, it can be used to define states.
No, that's the question we were discussing.
Yes, and
I
always
this
have
is a
an
very
impression.
unphysical situation. You said the box that you have drawn here is a box that is moving not with constant acceleration all the time, but it vibrates somehow.
No, the one I'm actually considering here is the one that accelerates uniformly.
All the time.
Well, from 0 to t within the integration domain.
In order to use these modes in the Rindler space, you must have acceleration that lasted forever.
As long as I'm calculating the probability transition within a range of times that are finite, it doesn't really matter what the mode happens to be after that. So
I still don't see how you define the modes in a uniform accelerated system.
We have been going through the discussion for many times, and I always have an impression that I somehow managed to convince you for a while, but then it doesn't last too
No,
long.
because you have all these paradoxes that the space is split into two pieces, and there is a horizon, and all these unphysical effects are there because you assume that acceleration is lasting.
Well, in a way, you could say that inertial.
Could you take oscillating box, for example?
Yes, the result would be exactly the same.
No,
Yes, you could.
It cannot be exactly the same because it's.
I can easily, what I can do, for example, let me.
Because then, when you have oscillating box, you have, for example, dynamical Casimir effect.
Yes, and I did actually do explicitly what you argue would be a physical thing to do, and I did the calculations on many occasions. You can take a box that moves along an oscillating trajectory,
Yes.
and goes with acceleration for a finite time, then stops, then accelerates back for a finite time, and stops accelerating, and you can actually continuously merge those elements and make the modes. You can stick the modes together in a way. You can combine them together, to have a evolution that corresponds to oscillating box, and
But
that's
this
roughly
is time-dependent system. There are no modes in the usual sense.
no, there are no modes. So what
Because everything is time-dependent.
this is going to be off topic, but I can tell you roughly what the method of that is going to be applied. So I need a precise diagram.
You have a time-dependent Hamiltonian.
What you can do, you can consider a resting cavity that starts to accelerate at some point for a finite time, the way you like it. Then the acceleration stops on a plane of simultaneity of the Rindler frame of reference that will be
Yes,
here.
but how do you find the modes during this acceleration period?
Well,
What is the meaning of modes in this case?
first of all, what you need to do is you have to take a quantum field in this part of space-time and to decompose them to any family of orthogonal modes. Could be eigenmodes, but they don't even have to be eigenmodes at all. You only have to decompose the field in any way that you choose that guarantees that it's complete. You have to find any complete decomposition of the field operator in this region. You have a complete decomposition into plane waves here. You have a complete decomposition into plane waves here, where you move with constant velocity. Here you can use the Rindler.
And there is some transition matrix which
Yeah,
describes the
yeah,
dynamical
So-
Casimir effect.
exactly. So you can, for example, you can take any decomposition here. It doesn't have to be anything really. It can be anything. We actually can choose it to be a Rindler mode truncated to that part of space-time because it's complete. Then what you need to do is to calculate the volume of
It's not complete over all space.
No, that's here. But you describe the field only inside the cavity.
But the state in quantum physics is described everywhere. Otherwise, you don't.
But the physical, what we are looking at is the content of the box. We don't care about what is outside. If you are interested
And
in
what are the boundary conditions of the box?
could be the one that we are using here, the Dirichlet boundary conditions, for example.
The wave function vanishes.
Yes, and in that case, the Hilbert space outside is decoupled. Yeah. So what you need to do is calculate Bogoliubov transformation from this base to this base, then calculate Bogoliubov free evolution here, and Bogoliubov transformation here, and you can calculate the final state, and you can convince yourself that you can take any limit, whether it's long-term acceleration or short-term acceleration, you can calculate that explicitly, and you say that you can see that transition is smooth. If you make this go to infinity, there is no sharp transition. There is no non-physical effect happening at infinity. It's like a smooth transition. Already when the acceleration is short, you already see the evidence of the dynamical Casimir effect or some other manifestation
Because
of
of
the
the
Unruh effect.
Bogoliubov transformation.
Yeah.
Particles are being created.
So just for the record, let's assume that I have convinced you for a while to this.
But if you have particle creation, then it's not easy to say what you mean by decay, because
Yes.
the number of particles changes.
So
Anyway.
in this particular model of interaction that I was talking about, I'm assuming a transition from 1 to 0
But
of the mode of the free field decomposition, which is not the diagonal one for the Hamiltonian.
and at what time? Before the
I started at time equals 0 and I finish at some large time t. Well, I can calculate for any time I want, but I know that for short times it's not really physical. If you want to go to the golden rule regime, you have to take t to be large. For small times, it's actually quadratic in t. For large times, it's
But
linear.
golden rule is valid for stationary systems, not when the Hamiltonian changes with time.
No, golden rule you can apply for the time-dependent perturbation as well.
Yeah.
No, but here the meaning of the particle changes when you go along this.
That is true. But yes, but I don't see that to be harmful to this analysis I'm doing here. Well, again, I don't have anything against doing the same calculation. I don't want to be too defensive about the particular model of interaction I have chosen, because this is not relevant. Sorry.
But maybe you can engineer this model in such a way that those two numbers will be equal. Maybe. You know, if you have different
Well,
information.
yeah, I just wanted to talk about that. Yeah, give me a second. Sorry, I have to go through those animations. I I'm not defensive about that at all. I mean, I take all the criticism. I understand this is just a toy model with all its flaws, but I don't really care, because what I care about is this transparency. And I don't care about how do you calculate those gammas. It could be more complicated way of doing that in other models, but they are still going to be there, and that's crucial. This is the point of the talk. So you can change the model to your favorite, you still get the same qualitative effect. Now, what does it really mean? Because we are considering a simple case of uniform accelerated box with a single particle in it, and we calculate the decay of that particle, and we assume that to be our clock. And we see that there is no simple transformation. You can't take a stationary box and just replace it with tau. It doesn't work. It breaks down at some point, and those accelerations where that appears actually are roughly 2 orders of magnitude above the level of the experiments that I mentioned in the beginning. Although that experiment did not have linear acceleration, only have a circular acceleration. I mean, there is a centrifugal force that makes particle go around in circles. So it's not exactly the same thing, but in a way, the level of accelerations is comparable. So probably if you accelerate a little bit more, you'll already see some deviations from the ideal formula. But somebody asked, can you compensate for that? If you know the rates, why not just taking your clock and you just have to re-gauge it somehow, renormalize it, of course. But if you know the path in advance, you know what effect to expect, you don't need a clock at all. If you know the path, you can just calculate your proper time, you don't need a clock for that. The idea of a clock is to have a device that you take on an unknown trajectory and get an outcome that tells you something about the trajectory that you didn't know before. It's supposed to measure the time along any trajectory you choose.
Yes, but correcting this outcome afterwards, after you understand what the physics of the clock really was, that's not a problem at all for me. I mean, the fact that sometimes the quantities you measure need to be corrected because you realize that the physics was more complicated.
But you use measurement device to measure things that you didn't know. If you know that you are going to measure something with your device and you know what the outcome is going to be, you know, I can suppose that I have a certain complicated measurement and I know that the answer is going to be 5. Then I can build a device that measures that. I can simply take a student, put him in a box, I will throw in a piece of empty paper and give him a pen, and he writes 5 on that paper and gives me back the card with 5 written on it. That's my measurement device. Right? It's going to give me the correct answer. But that's not what devices are for. I mean, he's supposed to, if I change the conditions of the experiment, he's still going to give me 5, whereas it's not a good outcome anymore. So your clock would have to be corrected for any path individually, and for that case, you don't need a clock at all. If you know the path, you can just calculate it. The clock is supposed to measure you the proper time along the unknown path. And certainly, even for the simplest case of uniform acceleration, there are problems. I don't even want to think what happens if you have non-uniform acceleration. That's going to be even more complicated. So in that case, you don't know what to do. Even the calculation is difficult. So in a way, I would say that, again, at some point, when those correction terms become relevant, things break down.
What is small here? In what units is the small? What is the unit of?
Well, the characteristic.
Or the wavelength of the?
No, the length. The characteristic quantities are length of the cavity and acceleration. So alpha times L over C has to be small. Then you don't see anything.
Relative to acceleration.
Yes. L is the length of the box or the size of the particle.
This is not dimensional.
This is dimensions.
C squared. C squared.
Yes. So that's basically it. The conclusion of the talk is very simple. It's this. So you can still keep in mind that all general relativity is actually based on covariant derivatives that are, roughly speaking, derivative with respect to some quantities like proper time. Which means that if you don't have a way to measure that, about physics that is unmeasurable, it's not really physics anymore. So you can ask to what degree it makes sense to talk about extreme non-inertial situations, knowing that you can't really measure them if you only have quantum devices. Classically, you can measure proper time. You can have an idealized device that measures proper time. In the real world, it's not possible. But that's quite an interesting conclusion. Like, you really have to think about what are you doing in physics, especially in gravity, to what degree it makes sense to talk about that when there is no way of measuring even such a simple thing as a proper time or proper length. Okay, that's it. Thank you very much for your attention.
May I answer the question?
I don't know who's in charge.
He is in charge.
May I?
Sure. Okay.
Always.
So there is additional interesting aspect to what you were talking about. This UNRU radiation, since it's a thermal state, means that for the realistic decaying system, the decay would be incomplete. In other words, even when T goes to infinity, there would be some probability of remaining in the excited state or
Fluctuation.
undecayed state.
But there is even probability of excitation in that case.
That's right. That's right. So, which is even more exotic, yes? Than what you're
Yes. So it's funny that those 10 to 15 Gs that were realized in the CERN experiment were only, I think, 2 or 3 orders of magnitude below the threshold where you actually see the UNRU effect. So I'm actually kind of interested in now maybe going to more realistic cases of actual QED calculation within a rotating frame of reference where you actually can see or predict where those effects will take over and maybe think about an experiment. I don't know.
So, building a lateral. So like,
Those experiments were made like 30 years ago or so. They are kind of
LJC
would clearly make it possible. I believe. Yeah, go ahead.
One remark and another thing will also be a remark. So remark number one, let's begin with this formula. You can imagine that you write number one between the integral and the square root.
Yes.
Then you use the formula for partial integration, change this one into t, and differentiate the square root. And this way you get another formula for the proper time, which actually exclusively depends on a acceleration.
Oh no, well there is a boundary term that if you take into account,
Yes,
it
but
cancels
keep in
out.
mind that saying that something does not depend on acceleration is a bit ambiguous.
No,
you have to be
no,
very careful.
I don't
what
agree.
you mean by
This is unambiguous. This does not depend on acceleration. You have to.
the whole thing, so the path from the with the fixed boundaries and the in the integral does not depend. So this is your
Yes. Yes.
point.
So in a way that example I gave with an accelerated clock, according to this formula,
Yeah.
the two clocks are going to give the same rate, whatever. If you can do your partial integration, it's still not going to change the answer.
Yeah.
Okay, and the second remark is so you have proved that measuring proper time using particle physics has certain limitations. For very large accelerations it may fail. That's true, but you can say it about measuring of distance. For example, in very high temperatures you cannot use a ruler to measure distances because the ruler evaporates.
For example.
Yes. But it does not mean that the notion of distance has to be revised in physics or
I'm not so sure. I'm not so sure because the notion of distance is only based on our experience in reality because we know how to measure it. You know why we use this? For example, you can imagine a situation where distance between Warsaw and Krakow is fluctuating by large magnitudes. If the reality was that way, if the space-time was time dependent, we would not even introduce the notion of distance. It doesn't make sense. If
Excuse
5
me,
minutes later,
it's even worse than that. It's not well defined. Because what do you
Yes,
mean by the
it's
distance
not well
between
defined.
Warsaw and Krakow?
Yes,
Between,
yes.
the Palace of
It's
Culture
not well
and-
defined, yeah,
and
but
Krakow.
approximately it's well defined for the like range of experience you have performed. So in the case of your evaporating ruler, you're absolutely right. It doesn't make sense to talk about distance if you can't measure it. I mean,
Well, in
philosophy, you can say-
astronomy, we measure distances using standard candles, yes, and there is
Yes.
always a question if the candle is a standard one or not.
Yes,
Supernova
yes.
is a standard candle, not really. And there's many papers about this, how to standardize supernovae. and to certain limit they can be used and adapted to its material. It's the same problem.
I think that the main problem here that you encounter is that you are trying to use the classical formula and apply it to quantum particles. There is no way to define velocity for a quantum particle. It's not a well-defined concept. It's only true in the classical approximation.
So the way I did that is, this is again a semi-classical approximation when you actually have a mirror, a classical boundary condition that you can keep under control. So you said that you are right that in order to accelerate a particle, you need actually a field or some sort of external potential.
And then velocity does not.
Yes, what we are having is we are having a box, and you assume that the boundary conditions hold, and we can actually modify them. We can make the box and shake it classically. So that is classical element that's standing behind the formulas.
But here, when you apply it to quantum field confined to boundaries,
yes,
the approximation that you can treat it, the boundaries classically fails.
of course. So that's also, well, but already within that approximation, the whole thing fails. So if you want to add some more failures to that, I agree there is more. For example, the box
It's
is
enough to have one failure. Failure is that you are using this formula, which is classical, and apply it to quantum objects.
Is there any quantum field theory which is relativistic and of interacting
But there's
particles,
no-
which is working?
Which is field theory, where velocity is not.
And this is of interacting field and it is working, and you can do something more than perturbation expansion?
Okay, let me put it this way. We are using our theories with boundary conditions and stuff within certain regimes. We don't know what's outside those regimes. I'm saying that if you take that theory and assume that
Yes.
you can apply it in outside of our regime, it already gives you a failure. Then clearly you can imagine that if the real theory that needs some modification of it in order to be applied to the regimes that I'm considering here, you don't want to miraculously reappear the proper time in your measurement scheme. This notion of proper time is probably gone forever. Even if you modify your theory, you wouldn't expect that somehow it recovers the ability to measure proper time. So
The question is proper time of what? You say proper time, and you define it along a trajectory. There's no trajectory in quantum.
I agree.
theory.
So
Therefore, the whole notion of proper time loses its meaning.
that's the technical detail I didn't mention. What we are considering is a uniformly accelerated box, and the proper time is the proper time of the inside of the box, exactly the line inside in the middle of the box.
But that does not
Correspond to
correspond to a particle.
Of course. That's what I said before, that the concept of path doesn't make sense in quantum theory. But we could maybe expect that somehow approximately the path makes sense. But even if you assume that approximately the path makes sense, you can't measure the length of the path because the mechanism breaks down.
It is like a hopeless project because in order to have these extreme accelerations,
Yeah.
you must really have particles,
That,
not classical objects.
yes, but the purpose of
Like
this
a
talk is
spaceship.
the
And
purpose of this.
therefore, you have many problems before you can treat them.
Yes, but the purpose of the talk is exactly to show that even if you forget about many problems, you get others that take over. So I agree, the project is hopeless.
Okay, but this is the same problem as this guy, so we can go to the guys of LHC and say you are not accelerating really particles because there are no particles, yes? They believe they do accelerate particles and collide particles, so this is within this framework, this
Yes.
what is.
They have very, very large accelerations there,
Yes.
and they still believe it's just part
But
of the
they
vacuum.
still believe that there are particles which are colliding. No?
Yeah, even more. They go back and forth between lab frame and
Yes.
moving frame, yeah?
Yeah.
Which is exactly
What he is doing here. So this is definitely not a problem of Dragan, but a problem of theory. Okay, I would agree. Otherwise, the theory which they are using in this LHC is also completely.
They are using classical theory to describe trajectories.
Yes,
And it works.
and it
And
works.
it works because at high energy, this is a very good approximation. But the point is that one cannot treat fundamental problems in an approximate way. That is something which may lead to these paradoxes.
Well, in a way you can't talk about any fundamental problems then, because always that we know are approximates.
No, but The point is that approximation should not spoil the fundamental question.
Yes, I know, I understand your point, but in a way I'm trying to say that within all our knowledge, there is no way of thinking about building a device that is actually capable of measuring this. For many reasons. You mentioned a few of them, I mentioned some others. The conclusion is the same. So we don't disagree with the conclusions. We may disagree with the way of approaching
Still the nuance lifetime changes when they are moving. And that is
and it changes when they are moving, but not
so this formula has been confirmed very well for uniform motion. Yeah.
For uniform, of course, yes. Well, I don't anyone, well, if you don't believe in Lorentz symmetry breaking, then
but when you talk about acceleration, then the acceleration mechanism becomes an extremely important issue. Whereas for uniform motion, you don't need any model of the force. And here you need the model of the force.
Yes. Well,
and that is why
so this model is semi-classical.
You cannot avoid answering the question, how do you accelerate the particle? Because accelerating the box is not the same as accelerating the particle.
Of course. Well, box is like special case of a potential, external potential, right? It's like
yeah, sure, but
very deep potential well. You could replace it with
time dependent.
Yes, you could replace it maybe with a harmonic potential, and maybe
since it's time dependent and you are talking about time, I think that this is not the best way to proceed. You are asking questions about time, and then you are using this time-varying situation, which is a hopeless task.
Well, the good thing about the Rindler frame of reference that it does have, I don't know, you may not be a big fan of Rindler frame of reference, but it does have a well-defined time, notion of time, because there is a killing vector that is time-like in that frame. So in a way, this is a stationary situation in a comoving frame of reference. But there is a well-defined notion of time in the uniformly accelerated case. I would have more problems talking about non-uniform accelerations, but for that case, I think I'm quite safe with that one thing.
Yes?
Thank you. May I think that this effect comes simply from the fact that these two fields transform differently under acceleration. Because you have one field which is massless and the second is with mass, and therefore they transform differently under the acceleration, and therefore this superposition, which was at the beginning the eigenstate of the whole Hamiltonian, is not the eigenstate in the accelerating frame.
This is, well, I haven't shown the explicit calculation, but this is not a problem. I could consider two identical fields if you want. We actually did calculations for two identical fields as well, and qualitatively it's all the same. Only what changes is the Mogulius transformation coefficients slightly, and that's all. Really, there's no dramatic change. There's just subtle correction. But you can take, the reason why we did not take massless fields, for example, is that for massless fields and that type of interaction, you get divergences, infrared divergences. You have to somehow cut off. So that's the only reason we used mass. And you can take both fields to be massive. That actually does not change anything. There is also a very nice candidate for your calculations. If you want to be more realistic, it's the 5-3 theory. That is a toy model of QED in many textbooks. Quantum field theory, 5-3 interaction theory.
It's a wrong theory, it does not get the ground state.
Or is it no 5-3 or
5-4?
5-4.
5-4 is good.
Yeah, 5-4. So, but again, the transition probability amplitude is going to change. I don't know why I didn't see that. But the general presence of the thermal state outside.
I think it's his argument that there are these two sums which were one involved in these two Fermi rules. One involved the summation of this modulus squared of amplitudes, and the second the same plus something. It's crucial because then, oh yes, this one.
From thermal state.
Because then you have to prove that for any possible interaction, this term with sine hyperbolic square vanishes. Okay.
This is basically the proper acceleration.
Yes, which is properly very hard to prove that it will for realistic theories. That realistic theories are exactly those for which the sine hyperbolic sine square vanishes. Okay.
So what specifically depends on the theory are those coefficients down.
Yeah.
But that general expression does not depend on
Thank you.
I would like to invite everyone
By saying that it's actually the same as being converted into a bunch of straight lines.
No, but what's wrong with this formula in the continuous version? Why do you deny the significance of this formula?
Because it does not depend on acceleration. In principle,
So
behavior,
So what? I mean, it's still the proper time.
it is the proper time. So that's the mathematical formula. That's the length of the path in space, right?
Yes.
But the question is, can you have a device that actually measures it? Which means, can you have a device that is completely insensitive to acceleration? Is it possible? All devices that we know are affected by acceleration. If you take a pendulum clock and make it accelerate, it's broken.
What about elementary particles?
Exactly. So the most fundamental clock you can think of is the elemental particle that is decaying. If even decayed particle turns out to be affected by acceleration, in contrast to this formula, then I should say that there is no way of building an ideal clock at all. Even if elemental particle that decays and that decays is used as a rate of proper time, even if that is not a good clock, then I guess we can say that there is no way of building a good clock that actually measures this. So this
this assumption that nothing happens at these points
Yeah.
is the origin of the twin paradox, simply. Because in twin paradox you have the same. You have the velocity in one direction, then instantaneous change of the velocity to the opposite one, and then you have twin paradox. So you cannot assume that nothing changes at this point.
Exactly. Well, with twin paradox is a bit different because, well,
Because you change the velocity, so you are not in the
No, but in twin paradox, you actually, even if you have a twin that measures proper times, there is already a paradox, right? And
it's
paradox,
because of this point.
because of these points, yes. But what I'm saying is that if you have acceleration like that, your clock is not going to measure proper time. It's not going to be even proper time. It has to be something else. There has to be corrections that depend on acceleration, and I'm going to show that there must be these corrections.
But in the twin paradox, we don't have to introduce such sharp changes.
No.
It's just two different paths.
Yes.
When the twins come together
Yes.
continuously, there will be a twin paradox.
Yes, of course. But let me put it this way. In the twin paradox appears already when you say that you have two clocks that are able to measure proper time. What I'm saying that even measuring proper time is not possible. So let me just give you one example. I always give it to students to make them realize that there is actually a problem.
To make it completely clear, it's not important that these changes are discontinuous.
No.
Yeah.
Even for continuous
Yeah.
motions, there is going to be a problem. So consider a very simple type of motion, a sinusoidal motion when the clock is actually oscillating. So the trajectory is, according to this formula, velocity is the derivative, and acceleration is the second derivative. And I can consider the following non-relativistic limit of that motion, where amplitude goes to 0, but frequency goes to infinity, in such a way that the product goes to 0, which means that both position and velocity go to 0. So the clock is technically resting, but I can take the limit in such a way that a times omega squared goes to infinity. I can always find a transition like that. It doesn't have to be infinity, I can make it sufficiently large, that's enough for me. In that case, position is strictly 0, velocity is strictly 0, acceleration is singular. It's oscillating very fast with very, very high amplitude. And, sorry? And
A is going to 0.
No, but the
No, it's not
amplitude,
going
The acceleration is huge.
amplitude of acceleration.
a times omega squared goes to infinity, which means that you have a device that is almost at rest, but it actually accelerates like crazy. And then you can ask yourself, suppose you have a second clock that is just doing nothing next to it, standing still. And you ask, is the rate of these two clocks going to be exactly the same or not? So you have a clock at rest, and the other one that is accelerating very, very fast, infinitely fast actually, and switching the direction of acceleration infinitely fast. And if that's ideal clock, it should work exactly as the one that is standing still. Now, is it possible to have a device that is insensitive to infinite accelerations? I don't know. I think not. Well, actually, I know, and I want to show that it's not possible. But this example already should make you doubt a little bit about possibility of using this formula, because according to this formula, this infinitely accelerating clock should go exactly as the one that is standing still, because there is no acceleration here. It doesn't care about acceleration. So, yeah, the question is, can you measure this? Can you have a device that you use to measure this? Now, there is another argument why this is a very good way. I mean, this is this idealized notion of time, simply because this expression is invariant under Lorentz transformation. Which means, if I have a path in space-time, maybe it's good if I draw this on the whiteboard. If I have any path in space-time, and I measure proper time, or calculate proper time between A and B, I get a number. This number is insensitive to Lorentz transformation, which means if I go to another frame of reference and observe the same trajectory from a different frame of reference, which is going to look maybe something like this. So it's the same path but viewed from a different by a different observer. A and B is here. If I calculate proper time here and proper time here, I get the same number. So people say that ideal clocks must be measuring something that is insensitive to Lorentz transformation, because, well, as all measurements, if you make a measurement, get a number, this number cannot depend on the observer who is actually looking at the device. And proper time actually has this property that is invariant under Lorentz transformation. But I'd like to say that this is not the only invariant that characterizes the that characterizes the path in space-time, and this is not so well known. I'm surprised I never found this in any textbook. But I can give you a simple example of other invariant along the path that depends on acceleration. So take for acceleration, which is basically derivative for velocity over proper time, and take a square of it and integrate it over proper time. Since this square of a 4 vector is invariant under Lorentz transformation, and proper time is invariant over Lorentz transformation, this whole integral is also invariant. Actually, it turns out to be proper acceleration integrated over proper time. Proper acceleration is acceleration experienced by the co-moving observer. And if you do simple transformation, you get this integral. Now, this integral also does not depend on the observer. You can Lorentz transform it and you get the same result. So, and more than that, this is actually dimensionless. This has no dimension, no physical dimension if you divide it by c squared. Or if you divide it by c, it's dimensionless. Which means that you can easily modify this formula using that invariant and get the test is, basically they have a decaying particle that moves with very high velocity and moves in a circle, basically in CERN, in the accelerator. And moving on a circle means accelerating all the time. And actually, these accelerations are quite high. The experiment apparently measures accelerations up to 10 to 15 or even more g, which is quite a lot. And apparently the decay rate of a muon is affected by the Lorentz factor exactly according to this formula, and no corrections to that formula are discovered in the experiment, even for accelerations up to 10 to 15 g. So apparently the decaying particles are very good ideal clocks that actually are able to measure this relation. Now, my talk is basically the purpose of this talk.
Perhaps that's not the general case, because in the accelerator, v squared is constant.
That is true. Yes.
Therefore, this is not the general case where you have v.
That is true.
Square changing.
That is true. So so I can't actually study this. I'm not studying this example in this talk. I'm studying the example of linearly accelerating particle, and the purpose of the talk is to show that actually every clock has to break down at some point, and every clock has to eventually depart from this formula. But it's not possible to have a device, physical device, that actually can measure proper time along any path. So the example what I mentioned before is that different clocks will behave differently for the case of acceleration, and you have to ask yourself, how do you actually build a device? Which clock mechanism do you choose to have a device that measures proper time regardless of its acceleration? And one thing I would like to notice is that this formula can't actually be derived from special relativity. You can't really derive the rate of accelerating clock. What you're saying is that if you have a clock that moves on a path that is curved, you approximate that path with a bunch of straight lines, and you say that on those straight lines, obviously the clock rate is known, it's just delayed by the Lorentz factor, but you don't know what's going to happen on those points where the acceleration is actually infinite. And you're saying nothing happens there. That the clock is not affected by those points. That's your approximation. And you approximate the real mechanism.
Will be given by Andrzej Dragan, who will tell us that there are no ideal clocks, maybe there are ideal watches.
So this is my work with my PhD student, Krzysztof Lorek. And it's also somehow linked to my previous work with guys from Sweden and England. And it's basically about quantum effects in relativity. And I would like to start with a quotation from this nice book by James Hartle. Very, very nice book of like first manual like introduction to gravity. And they mention the idea of so-called ideal clock, which is a device, hypothetical device that measures proper time along a path. So basically, if you have a clock that moves with constant velocity, special relativity tells you that it's going to be delayed by a certain constant factor depending on velocity, and the same factor, it's the same factor for all possible clocks. So no matter what device you take, if it moves with velocity v, the dynamics is going to be slowed down by the same Lorentz factor. However, if you take a clock and make it accelerate, special relativity doesn't really tell you what's going to happen. For example, if you take a pendulum clock, something else is going to happen to it. Then if you take an iPhone that also has a watch in it. So the mechanism of the clock specific mechanism can behave differently for the case of accelerating motion. It's a little bit in the contrast with what this guy is saying and with what most textbooks is saying about that issue. So they are giving a formula for proper time, which is basically an integral over time with this Lorentz factor. And let me notice that this expression does not depend on acceleration. I'm going to talk about that in detail. It only depends on instantaneous velocity of a device. And proper time is this so-called like length of a path in space-time, 4-dimensional length. And what this guy is saying that it should be noticed, emphasized, that these expressions hold even for accelerating clocks, even when the velocity is dependent on time. So they say that ideal clock can actually measure this thing if it accelerates. And there is a famous test of this relation for an accelerating clock, and it's described on another page. Let me just tell you what